Yeah, good morning. We were discussing feed-forward opamps, which also has two stages in cascade. Now, the tricky part is the feed-forward stage. That connects directly. Its input is connected to the input of the opamp, and its output is connected to the output of the opamp. Okay. So that depends on how you implement it. If you implement it using a differential pair, you could compromise the swing limit because then this stage could limit the swing limit, although the other stage is perfectly capable of giving a higher swing. So sometimes you can use this. This is basically the idea here is that the stage that connects directly from the input to the output, also called the feed-forward stage, that is required only for higher frequencies, right, around the unity gain frequency. So it's okay if you cut off some of the low frequency parts, because most of the low frequency loop gain is obtained by the cascade of these two stages. So as long as your AC coupling corner is such that the overall frequency response is not affected too much, you can use this one. Okay. So I will illustrate it with a differential pair, but the same thing can be used. Now, these are like specific IC design type techniques, so you can have lots of variants, but main thing is to understand the principles. Okay. And I won't go too much into the analysis. Whatever analysis we did for the feed-forward op-amp with the parasitic capacitors, that should suffice. Basically, maybe I will quickly recap. If I show the single-ended equivalent, single-ended op-amp, we have the cascade of two stages like that, and single stage that way. If I call this GM1, GM21, GM22, and you have some load capacitor which is due to the parasitic capacitance as well as anything else connected there, and you also have some capacitor over there. Okay. So with this, what will be the form of the transfer function? Let's say we ignore the load conductances just for writing a simplified expression. What is the form of the transfer function? What did we get? So basically, you will get something of this form. So you will have something of the form of 1 by s square. That's because of the cascade of these two. And this alone will give you omega u by s. Basically, around omega u, it is this part that is active. This can be written as a couple of different ways, or okay. So now, so basically what happens is the omega u z1 by a square, that term, if it is like that, and omega u by s if it is like this. So we are now of course talking about the magnitude of V naught by Vd. Okay. So this will be omega u by definition, right? That is that term alone. So the composite response would be that. Okay. So what I was saying was, if your AC coupling corner is below this, then you're not going to be affected by the fact that you AC couple this stage, right? Now, of course, in reality, you do have a finite DC gain. So what happens is that you will have at low frequencies, the gain will get limited. Okay. Now this crossover frequency where the minus 40 dB per decade curve meets the minus 20 dB per decade curve. What is it? What frequency is that? Huh? That is Z1, right? Okay. So now this we have already discussed. You can, where do you position Z1 with respect to omega u? Below omega u. How far below? So you have to position it below omega u so that your closed loop response does not have ringing and so on. Okay, that is you have sufficient phase margin. At the same time, if you position Z1 far below omega u, what happens? What did we say was the problem? So the DC gain of this part alone, assuming somehow we cut off GM21, we disable it, the DC gain of this part alone would be like the gain of a single stage, and it would have got limited something like this. It would be, it will get limited to something of that sort. So what did we say happens if Z1 is far below omega u? Huh? Why? Why does DC gain have anything to do with Z1? By the way, which is the, what is the frequency Z1? Which component influences Z1? Which components in the circuit influence Z1? What is the expression for Z1? Okay, I have some Z1 and I want to reduce its frequency. What should I do in the circuit? What is that? Increase C2. Okay, what else? Yeah. So GM1, if you increase, you will change omega u also. So let's say we don't want to affect everything else. So essentially, what happens is if this part, the 40 dB per decade curve that moves to the left, you will lower Z1, right? Okay. So that is, you can reduce GM21, reduce GM22, or increase C2. Okay. So now with this in mind, like what is the issue if Z1 is at a very low frequency? Let's say you make an amplifier with this and you apply a step. What happens? What did we discussed this, right? So basically there will be a slow settling component. So imagine that Z1 is at a really low frequency, like 1 hertz or something. Okay. So then what happens? Initially it is like this path is not there at all because you can apply a step to the, I mean, you make a unity gain closed loop amplifier and you apply a step. This voltage changes so, this current changes so slowly that it really doesn't count to anything. So it's like having a single stage op-amp reach steady state, and it will reach a wrong steady state based on its own crappy DC gain, right? Now, it's only after this voltage builds up to this, the current from this cascade of two stages builds up to an appreciable value that you settle to the right steady state. Right steady state meaning lower steady state error. So let us say that if you had only this stage, right? Let's say GM21, you could turn it off. You had only this stage, then, so I am of course talking about the closed loop response of a unity gain amplifier. Okay. So if we had only GM1, GM21 was somehow disabled, and let's say the DC gain of that op-amp was 10. Okay. So if you applied a unit step, what do you expect to happen? If you have a single stage op-amp with a DC gain of 10, okay, and then you make a unity gain amplifier with it, and you apply a step, what will be the output? It will settle to approximately 0.9. Actually, it will be 1 by 11. I think that will be the steady state error, but let's say 0.9. So that's fine. So This is what it will do. And the time constant will be related to omega u. Okay. Now, when you augment this, if this is very slow, what happens is, of course, this settles, and then after a long time, it will start creeping up to the right value. Let's say that when you add this stage, the DC gain becomes 100. Okay, what will be the steady state error in that case? 0.01 roughly. Okay, so basically it will settle to 1 minus 0.01, but very slowly. It depends on how fast this stage picks up. So you don't want to make this very slow either. I think we have discussed this before. You please refer back to it. So you want to keep it below omega u, otherwise you will have ringing and so on. Because if this starts giving you a lot of current while this one has not settled. On the other hand, if you make it very slow, you will have the slow settling component. So it's not very useful either. So you keep it a little bit below omega u, just to make sure that, I mean, as with everything else, you can decide by sort of looking at the overshoot in the step response and making sure that that's limited, right? That's how you did it in the simulation assignments. No? You made sure that the overshoot is, let's say, 5% of the step that has to be there, right? So that's how you choose Z1. So the bottom line is that in design, so in the two-stage Miller op-amp, let's say you had a poor phase margin, what all would you adjust? What would you adjust? In the Miller op-amp, you have poor phase margin, what component would you start like playing around with? CC, right? I mean, you can play around with many other things. Again, when I say we want to change the stability margin, the idea is you shouldn't change anything else. You shouldn't go and change every other characteristic of the op-amp. Now, if you change CC, yes, it will change the stability, but of course, GM1 by CC is the unity gain frequency. So, to a first order, if you change GM1 and CC in the same proportion, all other things will remain roughly the same. Of course, we know it doesn't remain the same because even the non-dominant pole expression has CC in it, right? So, similarly here, if you find that the phase margin is not sufficient, that is Z1, this 0 Z1 is close to omega u or maybe even beyond that, what will you do? How will you fix the situation? The 0 Z1 is, instead of being below omega u, it is above omega u. What will you do? What will you do? We just now talked about it, right? So basically, you either increase C2 or reduce GM21 or reduce GM22 or some combination of all of them. Okay. So that is something that you will have to do. So Z1 basically turns out to be right. So it's basically the gain of the first part is GM21 by SC2. So the current coming out of that is GM21 by SC2 times GM22. So when that equals GM1, right, that's when you have the 0. That's when this 40 dB per decade and 20 dB per decade lines cross each other. So this will be the 0 frequency. Okay. So, C2, right? Yeah, there is no C1 in the circuit, it's C2. Yeah. So to change Z1, all these three seem fine. Okay. Is there a reason to prefer one of these over the others? Are all of them the same, really the same? Will it affect anything else? What is that? Oh, why? It's you have to decrease the current. That is, you want to push Z1 to the right. Okay. Yeah. Yeah, that may be the case. So you can change only the capacitor. That is one possibility. Okay. The other thing is, what do you think the low frequency input referred noise of this circuit will be at low frequencies? What will be the input referred noise? Which component will it be influenced by? Yeah. Which one dominantly? So one way to think about it is you look at basically the output current of this op amp and then see which one dominates, which will be the dominant contributor to noise. So I will skip drawing the capacitor because I'm only, or maybe I will draw the capacitor. Let me do that. Say 2. Now I will terminate the output in a short circuit. Okay. And let's say, and of course I apply 0 volt to the input for analyzing noise. Now, what is a reasonable model for the noise of a transconductor? Again, I think we have discussed this before. So what's the noise model? What model should I use? I think you must have used this in the assignments also, right? What is the noise? So basically it will be 4kT GM. If nothing else is given, you can make transconductors with noise much more than this, but you probably cannot make it much less than this. But there may be some small factor, like if you use MOS transistors, you will get another factor of 2/3. Instead of 4, you get 8/3 and so on. But otherwise, this is a sort of standard model for noise, just like for resistors. So now I have four kT GM1 over there, right? And that directly flows into the short circuit. Okay. And here, and the same goes for this also. 4 kT GM22. Okay. Now, what happens to this particular noise? What will be the output noise spectral density because of this? Or maybe what is the transfer function from this current to that one? What is the transfer function from this noise current source to that one? So, this current, where does it flow? Into C2. So, what is the voltage that is created? If this current is called IS, what is the voltage that's created across C2? IS by SC2. And what is the current output from GM22 because of that? GM22 by SC2. Okay. So, basically, the output noise spectral density will have 4 kT GM21 times GM22 by omega C2 square. That is the magnitude squared of the transfer function, right? So, actually at low frequencies you get a substantial amplification of this noise, okay, and plus 4 kT GM22 plus 4 kT GM1. So, this is the output noise current, okay. Now, if you want to refer it to the input, what do you have to do? Basically, first you have to find the transfer function from this voltage Vd to the output current, because we took the current as the output, it is simpler, right? So, what is the transfer function from that voltage to the output current? So, V out by Vd would be GM1 plus GM21, GM22 by SC2, right? That's it. No, this is the transfer function of the, sorry, this is the current output by the voltage. Okay. Now, this one at low frequencies, what is it? At low frequencies, what is it approximately? GM21, GM22 by omega C2. Okay. So, what will be the input referred noise spectral density? So, basically this whole thing divided by the square of that. Okay. So, at least at low frequencies. So, what do you have? You have 4 kT by GM21 plus some things which you will see will have a relatively small value, right? Because as omega comes to 0, this will get multiplied by 0, whereas this one will always be there. Okay. So, at very low frequencies, the noise tends to be dominated by GM21. Okay. So, this means that although you can change the 0 Z1 by tweaking GM21 or the capacitor or GM22, probably better not to touch GM21, or rather GM21 should be determined by your noise specification. Okay. Is this clear? So, if you lower GM21 or increase C2, you will reduce the value of Z1, but one of them will actually increase the input referred noise. So, anyway, I mean, we can't discuss every possible scenario, but typically whenever you find yourself in a situation where your design meets most of the specifications, one thing is not met. The best case is if you find some knob that changes only that. Okay. And of course, if you have actually optimized the design reasonably, maybe not the global optimum, but at least you have taken care to optimize, it will become very hard to find this knob. Okay. Typically, what does optimum mean? That means you can't go further. If you have optimized it to some extent, typically what it means is that all the values are such that if you turn something, it will make something worse, maybe something else better. Okay. It's only when you are very far from optimum that you can find one magic solution that will reduce it. Okay. When you're closer to the optimum, it's not that easy. You might have to change many things. This again is not specific to circuits. This is for everything. Okay. So, this is about the feed-forward op-amp, and we've already discussed the common mode feedback and so on. So, any questions on any aspect of fully differential circuits? Just some number to start with. Okay. So, basically, I think I just chose it so that the lower the VD sat for a given current, you have the larger transistor size. Okay. And the first stage current is likely to be smaller anyway. So, if I gave 250, probably you'll find that the sizes are even smaller than the minimum width or something. So, with that, I think I just somewhat arbitrarily chose some voltages. Okay. Anything else? Any other questions? No, I think we've had enough of op-amps. We know now how to design any type of op-amp, or if you see a new one, you will be able to, based on these principles, understand how it works. Because in the literature, you find lots of different topologies, which may or may not fall into the standard ones, but there'll be some small tweak, like for instance, to cancel zeros or something. I think those things you must have seen in the assignments, right? There are many ways of, if you have Miller op-amp, there are many different ways of not having that right half plane zero, right? There are at least 2 or 3 different ways. They involve a current buffer or a voltage buffer or things like that. Okay. And in the assignment also, I think I asked you to try, right? To see did you see any improvement by connecting it as a current buffer, or did it make it worse? The first stage is a telescopic cascode. So you can connect the Miller capacitor to either the So first of all, okay, there is one more diversion. This is the output, and you make some amplifier with it. It doesn't matter what it is. Here I am showing an inverting amplifier, so you know how to calculate the loop gain and so on. Okay, and of course you would have this capacitor, and you know that in the loop gain, this will produce a right half plane 0. Okay, and the right half plane 0, what does it do? What is the consequence of having a right half plane 0? It reduces the phase margin. So in the frequency domain, you can see a right half plane 0 causes a further phase lag. So it reduces phase margin. In the time domain also, you can, what do you expect to happen? If you have in general, if you have a step and your transfer function has a right half plane 0, what do you expect in the step response? There will be an undershoot. Basically, this initially goes in the wrong direction before taking off in the right direction. Okay. So that is characteristic of the right half plane 0. Okay. Basically, you have 1 minus s by z1 where s is positive, right? So what does it mean? 1 minus 1 by z1 times the derivative of whatever else is there. Okay, the part without the 0. So essentially, this is like you're driving a car, you start going up a slope, the speed starts decreasing, and then you start braking, right? You should do the other way around. If you had a right half plane 0, that is like predictive based on, sorry, if you have a left half plane 0, it's like prediction. When the speed is decreasing, even if it is not decreased below the desired value, the fact that the speed is reducing, you are reacting to the derivative, right? The fact that you have s here, this means that you are reacting to the derivative. If you have a left half plane 0, that means that the moment speed starts reducing, even if it is not below the target, you start accelerating. If you have right half plane 0, it's the other way around. I mean, it's a stupid thing to do, but of course, sometimes, I mean, if you have a right half plane 0, you have it. So now how do you fix the situation? You want to get rid of the right half plane 0. What are the possibilities? I'm sure you have seen all the circuits. Huh? Yeah. So one of the things to do is connect a zero cancelling resistor. Okay. So what is the difference between these two? If you just look at the op-amp transfer functions, what will be the difference between this and that? I mean, is this some magic bullet that fixes everything, or what changes? So this will be a second order transfer function. I mean, assuming you have C1 and C2 there, right? It's a second order transfer function with a right half plane 0. Now here, what you get is what? You have a third order transfer function, but you can cancel the 0, or you could even move the 0 to the left half plane. Okay. So what is the value of RC required to make the 0 go to infinity? That is for the 0 to disappear. 1 by GM2. Okay. Right. So we'll see. We'll just discuss why 1 by GM2. So, but anyway, that will make the 0 go to infinity. But if you use a larger resistor, it can even move to the left half plane. Okay. But of course, if you overdo that, what happens is there will also be a third pole that is created that will move to lower frequencies. But in many cases, you can find some RC that works better than the case without RC. Okay, so that's why we use this. What else is there? What other possibility is there to make the zero disappear? What is that? Yeah. So all these, again, I don't know if I had an assignment in one of our assignments, we had this, right? So why do we get a zero? Because there are two paths. Okay. So somehow if you break that, you can get rid of the zero, and based on that, one of the ways to do it is to use that one. Okay. So you can see if this is VO, this will also be VO. So the current flowing through CC will be the same, but that will not get injected into GM2. Okay. Of course, this assumes that this is an ideal buffer, that itself is hard to make and so on. So there are those difficulties. And another one is on a similar principle. What else can we do? So instead of connecting this here, you connect it to ground and look at whatever that IC is and feed that here. So again, there is no feed forward from this to that. Okay, so it has become unilateral and then the zero goes away. Okay. So now what I was referring to was, how would you implement this current control current source? What is the, well, I mean, with transistors, how would you implement a current control current source? What do you need? Common gate. Okay. So now this particular one, this actually is not very practical, because remember this voltage buffer, whatever swing V naught has, it has to support that, otherwise it will not work. Okay. So now we know that the standard source follower, its swing limit is so poor that if you have a rail to rail type stage here, if V naught goes almost to the rails, you will not be able to make a buffer that goes to the rails. Or you have to make the buffer so complicated that it will have its own poles and zeros and it becomes a mess. Whereas this other one, you can implement for free, more or less. This is not a scenario. Let's say that we have a cascode for the first stage, right? We have a two-stage opamp. Whose first stage is a telescopic. Oh, I should have also put this. And these are biased at some voltages. Okay. So we have this cascode stuff, right? So now normally, CC would be here, right? So what next? Why did I walk through all this story? What am I getting at here? I said something about a current buffer, then drew some 2 copies of the two-stage op-amp, the telescopic cascode first stage. The thing is here, what do we need? So this current control current source, that is a cascode. I mean, that is a common gate amplifier, right? So that means that you should connect CC from the output through a common gate amplifier. If it is NMOS, it will be like that. And this should go to the first stage. If I call this VO1, it should go to VO1. Okay. Or I could have a PMOS common gate device. I have not shown the biasing. but this is a common gate device, common gate amplifier, and the drain of the PMOS should go to VO1. Okay. So what next? Yeah, that is ground, right? What is the impedance looking into the common gate amplifier? That is 1 by GM. Ideally, you should get 0. In reality, you will get 1 by GM. Okay. So what next? Where is the whole thing leading? I mean, it's just a pointless story that's going nowhere, is it? Yeah. Yes, please continue with the story. So, okay, at least look at this part of the circuit. What is this? So, if you look at M6 or M8, you already have common gate amplifiers, right? That is, if you connect the input to the source, the output is already connected to VO1. So, instead of connecting CC like that, you can connect it here or there, or maybe connect half to either one. This is also something that works. So, the point is now you didn't waste bias current trying to make a current buffer. It was already there. Okay. So, basically it comes for free. So, when you get something for free, you just take it, right? Oh, sorry. Yeah, of course. Thanks. So, this should no. What is the swing at these nodes? What should it be ideally? Why? No. What is the swing? Okay, forget that new op-amp. What is the swing at the source of M6 and source of M8? What should it be? If you have a cascode, what is the signal swing at the source of the cascode? Hmm? Yeah, I mean, is it high or low? It should be 0 ideally. If the common gate amplifier was an ideal current controlled current source, it would be 0. But the swing is very small. So, basically, the swings here are very small. So, this won't do anything to it. Yeah, right. Correct. So, now you are talking about basically the cascode's input impedance is 1 by GM6 and there it is 1 by GM8. Whether that is sufficient for the value of CC you have, that is something you have to check. Okay. So, it could be that your original design for whatever reason has very small current in the first stage and very large current in the second stage and a very large CC. Okay. So, whenever we say the impedance is small or large, this common gate impedance, when is it small? It is small when it's compared to the impedance of whatever is connected in series, right? So, if the impedance of CC is very low and the GMs are very low, then it may not work, okay? Because this is not an ideal current controlled current source, okay? So, it's like having this like everything else, right? You're having some resistance there. So, that will make it behave non-ideally. That is something you have to look from simulation. So, at least in the exercise, I think I had asked you to just connect it and see without doing anything, making any other changes, if the phase margin improved or not. I don't know how many of you tried it. The two-stage op-amp. What happened to the phase margin? Did it change or which way? Did it make it worse or better? better. Then why I'm getting no answers to this question? Why is that? Which one? These first two meaning? This one. That may be the case. Yeah. That is, I mean, depends on the specific specifics of the circuit. Okay. This one was not implemented, right? I'm talking about the transistor level assignment, not the in the ideal case, of course, all of them work. In the transistor level op-amp, you have a telescopic cascode first stage, right? So what I had asked was to try and connect this here and there and see what the phase margin is. I don't know if you tried that. If not, you try it out and see. Okay. Of course, with the ideal control sources, all of them will make the zero disappear. That's not an issue. Okay. So the thing is, it is possible that this gives you a better phase margin, and because essentially you are not making anything new, you already had every component on the right side, you already have on the left side also. All you do is split CC and then connect it to the tube sides. Okay. So any other questions on op-amps, differential pairs, common mode feedback? Okay, basically if you have a fully differential op-amp, you just start with the differential and common mode half circuits, and what you get will be for the common mode some feedback loop that you have to analyze, and for the differential picture you have something that you analyze separately. Okay. Any questions on any aspects of op-amp design? Now one thing, I mean, this is just information. So in all the examples I have used NMOS input stage, but you can also use PMOS. Which one would you use? Depends on the. So one is, of course, so the input differential pair, it can be PMOS or NMOS. Then if it is PMOS, VCM limit will be close to ground, and if it is NMOS, VCM limit closer to VDD. Okay. So this may be a requirement. Sometimes you may have to support a common mode that is very low or very high. So that is one reason. There is also another reason which is different. That is in that it turns out in most of the at least longer channel processes, the flicker noise of PMOS is lower than the flicker noise of NMOS. But this is not a universal rule. Flicker noise is not a fundamental phenomenon, right? It also depends on details of the foundry and so on. Okay. The main reason for flicker noise, the main difficulty in any processing is you have a surface that is interface between two materials. It is very, very difficult to keep that clean. Okay. Whereas inside the volume, inside the bulk of the material, things can be perfect. Okay. Or at least close to being perfect. So any phenomenon that occurs at the surface is prone to garbage like flicker noise. Now it turns out that at least in many processes, I am not a processing expert, but in the NMOS, the channel is very close to the surface. Whereas the PMOS has something called buried channel. Okay. So there will be some other implant on top of it, and the actual inversion layer is not right at the silicon insulator surface. Okay. So that's why, and I also said that basically it's because of this trapped charges at the surface that you have all these problems. So somehow PMOS has lower flicker noise, but this is not a universal truth. Okay. So don't be surprised if you find a process in which NMOS flicker noise is lower or the two are about the same. So this is one of the reasons why in low frequency, low noise circuits, you may prefer PMOS input pair. Okay. Any questions? Anything else? Right. Yeah. Okay. So let's see. So always we have a voltage source at the output, which drives some current. And we calculate the impedance from there, right? So this is VG78, this is VG56. And then we have some voltage source, some terminating voltage source, which keeps this, keeps all the transistors in the saturation region. Okay. And then I have some V test there. Okay. So now what happens? So first of all, if you look at the contributions because of these, right? So that is just a cascade current source connected to the output. So what will be the part of the current flowing this way? So basically it is Vt divided by the cascade output resistance. So it is Vt by, let's say, GM7, RDS7, RDS3. Okay. So this is M3 and this is M5 according to my usual notation. Okay. Now what happens to this side? So we have M1, M2. So now if you, this is a little somewhat confusing, but essentially if you have Vt here, you get Vt times some number, let's say alpha at this node. Okay. So the effect of that is basically if I'm not mistaken. So you have these, right? So let us say for instance, M1 and M2 had infinite output resistance, just for argument. What would be the current flowing that way? What would be the current flowing there? So it will just be Vt divided by the cascade, this one, right? So that will be Vt by GM5, RDS5, RDS9. Okay. So now, I mean, this is not quite superposition, but just for simplicity, I am saying you assume that you have infinite output resistance for everything, but only finite output resistance for this. Okay. So then what will be the current flowing here? Or what is the resistance looking into the drain? It is twice RDS1. This we have seen, right? Basically, this M2 is degenerated by 1 by GM1. Okay. So if you look at GM2 times RDS2 times the degeneration resistance, you will simply get RDS1 plus RDS1, that you can't neglect here. Okay. So this is 2 RDS1. Okay. So whatever this voltage is, Vt times alpha by 2 RDS1 flows this way. But again, the same thing goes that way, right? And then gets reflected. So the current mirroring effect is still there. But the whole thing, the net result is the conductance due to, so all the conductances are in parallel, right? It doesn't matter how you add them up. So you will get, that's true. If you look at the current component, half of it goes up and the other half goes down. This is just like in the regular simple differential pair also, it's the same thing, right? Although you get GDSP plus GDSN, the part that goes up is GDSP plus GDSN by 2. The part that goes down is GDSN by 2. The same thing happens here. Is that okay? Anything else? Okay then. See you all.